All right, so let's look at labeling the angle. So it says here that the angle is 32 degrees with the ground. So we're going to go over here to this right-hand side, and we're going to label this angle as 32 degrees. And then it's telling us here that the actual ramp itself, so the diagonal distance here, the ramp that the car is traveling on, is a length of 113 feet. So it should be our hypotenuse that is labeled as 113. And what we're interested in finding is the height that the car is from the ground when it launches. So the car is traveling up the ramp right here at the top of the triangle when it's going to launch into the air. So the actual distance it is from the ground at that point, we're just going to label this with a little lowercase h, not to be confused with like the capital H that we use for hypotenuse, but just a little small h to represent the height of the ramp. That's the side that we're interested in finding. All right, so let's take a look here at part 2. It says we want to think about which one of our trig ratios, sine, cosine, or tan, would be best to use to solve for the height. And so I want you to think back to what we talked about yesterday with SOHCAHTOA. Think about how would you name the two side lengths here that we have labeled, and based on what those two labels are, what would be the appropriate function to use? So I just want you to think about that for a moment and go ahead and write your thoughts down on your paper. All right, so if we think about the labels here, so what we would actually call these two sides. So I'm going to put my little star next to that angle of interest that we know that 32 degrees at the bottom. And so from that star, this side over here, the height that's completely on the opposite end, we know we would label that as our opposite side. And then that longest side, that diagonal side here, the 113 feet, is our hypotenuse. So which one of these did you choose? Which one has to do with the opposite and the hypotenuse? Go ahead.
Sine, because it has no adjacent.
Wonderful. We're not doing anything with the adjacent side. We're interested in sine because we know the hypotenuse. And want to find the opposite. And so a couple of notes, this was just directly from what we did yesterday. Our definition for the ratio that we're using sine to describe is that the sine of our angle is equal to the opposite side over the hypotenuse. So we are going to use that to now help us write an equation for using the trig function that we chose, sine, and then we're going to solve it to find the height of this launch ramp. So all we need to do here is just plug the pieces in based on what we see in the picture. So it's not the sine of theta. We actually know the angle measured here is 32 degrees, sine 32 degrees. And we know that our opposite side, what we're solving for, I'm just going to do the little lowercase h there, not to be confused with the hypotenuse, but that's what we're describing for height, but it's really the opposite side. And then we'll go ahead and divide that by our hypotenuse, which was 113. Now we want to think about solving this using algebra. We just want to get the variable part by itself. So what can we do that would help us to get rid of this 113 in the denominator? What would we do, Remy? Yeah, so you mean the 113?
Oh, yeah.
Yeah, so it's kind of like, we've seen this before, it's been a little while, but if you have something in a denominator and you want to get rid of it, or if you want to cancel it from your denominator, we're going to simply multiply both sides by whatever that denominator value was. So if we think about what's happening here on the right-hand side, if we do the height, and then we divide by 113, and then we multiply by 113, those are going to cancel each other out, and we're just left with the same thing we started with. Well, because it's an equation, whatever we do to one side, we have to do the same thing to the other side. So our final calculation is going to be 113 multiplied by the sine of 32 degrees. And for this final step, we go to our calculator. Now you can do this on your graphic calculator quite easily. A scientific calculator will work as well as long as it has the sine, cosine, and tangent buttons. And so I'm just going to model up here what it would look like on your graphing calculator. How we would want to type this in is I'm going to start with the 113, and then I'm going to click my multiplication symbol, and we're going to look for the sine key. So sine, cosine, and tangent, they're just two spaces above the 7, 8, 9. I'm going to go ahead and hit sine, and it was 32 degrees. And so we see that that should be about 59.9 feet. So what I forgot to mention when we first started this, before I did the calculation, is that to do it accurately, we need to make sure that our calculator is in the correct mode. And so you'll notice here that mine is in degrees, matching with the fact that this angle is measured in degrees. So let me show you how to adjust the mode. If you just type that in, and if you got a different answer than me, we need to turn it to degrees. So the way we do that on a graphic calculator here is we're going to go ahead and press the mode key, which is right next to the second key. And if you've never gone in and turned it into degrees, the factory setting on these calculators is actually the other option, and so we have to change it. And so if you use the little down arrow to get to that row, and then I'm going to go ahead and click the right arrow so it's blinking on top of the word degree, and then we can set it to degrees by pressing enter. All right, so now we are in degree mode. Now to get out of this menu, to get back to the home screen, we're going to press second mode, which is actually quit, and that gets us right back here. So if you didn't get the same answer I got, go ahead and try typing it in again, and now we should get the same thing. If you have a scientific calculator today, if you're not sure how to turn it into degrees, we'll have a little time here at the end of the lesson. Just raise your hand, call me over, and I can look at that process with you. All right, so let's go ahead and transfer this to our paper. So it was about 59.9 feet is our final answer. All right, so we just did a little bit of work here with the launch ramp. What we're going to continue with now in the second piece of this is to look at the landing ramp. So let's see what information we have there. So that landing ramp, it was actually constructed on a barge on the water. And so the engineers, they had limited horizontal distance for the ramp. And they needed to have a height of 98 feet from the ground with an angle of elevation of 36 degrees formed with the ground. What we're wanting to find this time now is the horizontal length of the landing ramp. So horizontally, how long was the bottom part of it? So we're going to draw a picture again of the landing ramp. We're going to label all of the information they've given to us in the problem. All right, so let's have our triangle picture here. Let's orient it now the opposite way. So we can think about, okay, so this was the launch ramp, flying in the air. I'm going to land here. And if we start to take a look at some of the labels, it says that this one needed to have a height of 98 feet. So we can go ahead and label that vertical distance height. And it says that it's an angle of elevation of 36 degrees formed with the ground. So if we want to try to find the angle down here formed with the ground, this right here is what we call an angle of elevation. So from this point here at the ground, like what is the angle that's looking upward at a higher point? And so we'll go ahead and label that as 36 degrees. So I'm just going to make a little note here. So this is what we would call the angle of elevation, is the one that's starting on the ground looking upward. There's actually another way that we can label the angle here up at the top that We're not using it in our problem right now, but you are going to see this in one of your homework questions. It's called the angle of depression, and it's just going the opposite direction. So here's what the story is going to be in your homework assignment. We've got Juliet standing at the top of the balcony, and we've got Romeo down below looking up at her. And so she's standing here at the top. The angle of depression of Juliet looking downward toward Romeo, where he's standing over here, the angle that you would label is actually the one up here at the top. So keep that in mind. These are just some phrases that sometimes show up in these word problems where we have to turn it into a picture. Okay, let's label the part that we're looking for. So we want to know this time the horizontal length of the landing ramp. And so I'm just going to use the capital L that they have up there in the problem. And that's because it's sitting on top of this horizontal barge. And I'm going to attempt to show that here in a different color. So like, let's say that this green represents the length of this barge that it's sitting on. And there's actually water then on both sides. Okay, so we've got water here. So we're going to have a little bit of distance on that barge for him to stop. But what we're going to be kind of investigating is, first of all, what is the length here of this piece? And then we're actually told the length of the whole barge, and we're going to be able to figure out like how much time he actually has to stop before going into the water, which would not be good. All right, so here's our situation. We've got our picture. I want you to go ahead and answer questions 5 and 6. So you're going to decide again what trig ratio would be appropriate for this scenario, and then you're going to write the equation and solve it to find the horizontal length of the landing ramp. All right, so we're going to come back to check in on this one. So based on the way that we have this picture labeled, which one of the trig ratios did you choose here? So did you choose sine, cosine, or tan? And you can just say out loud. I know a lot of you got it written down. Which one did you pick? Tan, yeah, that would be the one to use here. And so it's really just dependent upon where is that angle that we're interested in, where is that star. It looks like we know the opposite side, and we're looking for the adjacent side. So the only one that uses opposite and adjacent is tan. So we're using the fact that the tan of some angle theta is equal to the opposite side over the adjacent side. All right, so in part 6 here, we're just going to go ahead and plug the numbers in. So we've got tan 36 degrees. This time is equal to 98. And I'm just going to call it L for the side that we are looking for. You could put an X there. Some people put an A there for adjacent. That's fine. We're still going to get the same numerical answer at the end. But notice how this time, the variable, the piece that we're solving for, is actually on the denominator. And so that's going to cause a slight change in how we end up solving for it. And so the first step is similar to the last problem in that we want to multiply both sides by something to get rid of what's in the denominator. But what we have to multiply by to get rid of it is we have to multiply by the denominator. So instead of multiplying both sides by 98, that's actually not going to help us at the start here because it's not going to make the 98 cancel. If we multiply both sides by 98, then we have 98 times 98 divided by L. We still have a fraction. So we want to actually multiply both sides by the L. That's how we're going to get that to cancel. Now I'm going to write off to the side here what we're left with. So it's really L times tan of 36 degrees is equal to 98. Now we still have one more step to do because the L is not by itself yet. So this tan of 36 degrees, that's just representing a number. It's just some decimal value. In fact, you can type it in your calculator and see what decimal value it is. But it's just like we have a variable being multiplied by a number. And so just like we've always done in the past, if we want to get the variable part by itself, well, we have to divide both sides by whatever that number is. In order to avoid rounding on top of rounding on top of rounding, it's really helpful here to actually wait until the final step before you type it into your calculator. So here's what that would look like, keeping it in exact form as long as we can. We're just going to now divide both sides by tan of 36 degrees. When we go into our calculator, we'll still make sure that we're in degree mode. This one is going to be a little different now because it's involving division. Oh, what's our angle? 36. I know it's not 90. All right, so 98 divided by the tan of 36. And we can round this one again. Let's say that it's about 134.9 feet. That's that horizontal length of the ramp, 134.9. All right, so in the last part of the problem down here, number 7, so here it's telling us the total length of the landing barge. So if you look back up at this picture, the part that I highlighted in green, that is the floating barge. It's actually 200 feet long. We just found out that the horizontal length of our ramp is 134.9 feet, so we're going to have a little bit left over. What we want to figure out is what is that left over. So how many feet does that give Travis to stop the car before hitting the end of the barge? All right, so if we subtract that horizontal length of the ramp from the total length of the barge, we see that we have a little bit of room here, not a whole lot, but it ends up being about 65.11 feet. So that would represent like this piece here, 65.11 feet. All right, seems like a pretty scary stunt. I don't think I would do it. But I bet maybe some of you would. Would anyone do it in the room? A car jump? Maybe. Okay. All right, let's go ahead and turn it over to the back. All right, so we really have 2 learning targets for today, and we're going to sort of just combine them together in this important idea box. So what we were looking at today was modeling situations using equations with trigonometric ratios, and using trig equations to solve for missing sides of a right triangle. All right, so let's just call this. We're going to say here that today we were writing equations and solving for sides. All right, so the first step that we did today from our scenario was draw a picture. And I'm going to add in here that we also put in our labels. So with that initial picture, we're trying to label the pieces that they've given us in the problem. So what's the angle that we're interested in that we're going to label? What are the sides that we know? What's the side that we're looking for? All right, the second thing we did is we need to choose our trig function. And that's where we're going to think about SOHCAHTOA to help us figure out what are the 2 types of sides that we're dealing with. That's going to help us to know, is it sine, is it cosine, or is it tan? All right, step 3 was just to write our equation, plugging the actual numbers, plugging the actual values into the problem. And then step 4 was to solve for the answer. And that's where we always multiply both sides by the denominator value first. Depending on where the variable was, it either took us 1 step or 2 steps to solve for our final answer. We go to our calculator, make sure that our calculator is in degree mode to get our final answer at the end. All right, so I know we did 2 examples here already on the front side. We're going to actually put in a third situation, a third example picture and sample equation. This one is a right triangle here is going to have the right angle in the lower right corner. And I'm going to switch this up a little bit. So we're going to have the star angle that we're focusing on is actually going to be the one here at the top. So I think we've seen a lot of scenarios where it's down here at the bottom. Well, when you get to that Juliet and Romeo problem, and you have the angle of depression, that Juliet is looking down at Romeo, your star angle is actually going to be here at the top. And so I'm going to go ahead and label one side length here that we're given in this problem would be 12. And then I'm going to label an X like we would be looking for the hypotenuse, so that's the missing side. And notice that where that star is labeled, that's going to determine where the opposite side is. So this opposite side is actually the one at the very bottom now, because it's completely opposite of where that star is labeled. That makes the 12 the adjacent side. So adjacent means right next to. It's the other side of the triangle that's like right next to, touching the star angle location. And our hypotenuse is always our longest side, and that's the long diagonal side that we're searching for. Okay, so with this sort of setup, what one of our trig functions would make sense to solve for x? Go ahead, Daniel.
Cosine.
Or do cosine. So we have cosine of whatever that star angle is. We know that it's always adjacent over hypotenuse, so in this case 12 over x. We're not going to go through the rest of the set solving here. I didn't tell you what that star angle was, but because the x is in the denominator, this is one where we would have to multiply both sides by x first, then divide both sides by the cosine of the angle. So this would actually be 12 divided by the cosine of whatever the angle is to solve for the missing side. Now, one other little thing I want us to make a note of here, this is going to help you with the first problem in your check for understanding. And let's not use the star symbol. What that fact is that the shortest side of your right triangle is always opposite of the smallest angle. Whoa, what am I writing? Sorry. Okay, let's find our page. Smallest. My brain did something really strange there. The shortest side is always opposite the smallest angle. And if you think about that statement, it makes sense if we were to have a really small angle. So let's see if I can even draw one that's really small. So let's say that's like our horizontal length. I'm going to try to make like a really small angle right here. It's a really teeny tiny angle. It's not elevating very much, and so the side that's on the opposite of it is, of course, going to be like a really small side, or it's going to end up being the shortest side. So keep that in mind as you're looking at the first problem here in the next section. So we're going to go ahead and take a look at the check for understanding problem. There's really three different problems that we're going to look at. This is going to allow you to try out and practice the different skills and equations that we talked about. All right, guys, so as you're getting started and everyone's had a chance to take a look at number one, let's just touch base real quick about this picture here. So this has to do with that fact that the shortest leg of the triangle, or the shortest side, is going to be opposite the smallest angle. So when it tells us here that our angle is 36 degrees, that's going to be the smallest angle of the three. Because if we were to think about subtracting from 180, so we'll subtract our 90-degree angle that's a given because it's a right triangle, we'll subtract our 36-degree angle, and the resulting angle, I think it's 54, just double check that. Yeah, it's 54 degrees here at the top. So just by doing that quick check, we can see, okay, that's 36 degrees. This is our smallest angle. And so then it says a right triangle has a short leg that is 7 units long. So some people call this the vertical and horizontal sides, they call these the legs. So this is saying, okay, well, the short one, the shortest one is 7. That one's going to be opposite of the smallest angle. I'm just going to make a note here. This is the shortest leg. Or you could even just say the shortest side of the triangle. So it looks like here we wanted to draw a picture, which is what we have here, and then we just want to find the length of the hypotenuse. So a little different than how some of the questions were yesterday. It's not always necessarily going to ask us to find every missing side and every missing angle. We're just going to focus on what's the piece that it's specifically asking for.